Okay, so we are about to continue with Benjamin with binomial sums and Mellin asymptotics.
Second. There we go. Okay. Thank you very much. I'd like to, in this talk, basically show you something that I think might be useful to some of you. It's a new tool that helps with computations with asymptotic expansions, in particular in the context of a setting where you're interested in exact bounds. So not just O bounds, but actually bounds where you know the constants and everything is exact. Let's see whether this works. Right. This is a story in 3 acts. And in the first act, I'd like to motivate why we want to look at this sort of thing. And there's a quick activating question for the audience. I'd like you to guess what sort of lattice paths are we looking at here. So this is the class that I want to analyze. Can you spot the unique feature that they all have? Exactly, single maximum. I've made it look like little mountains where the sun rises behind the highest peak. And indeed, this is the class that we want to look at. I've called those, and the name will only appear like once or twice in this talk, max peak unique Dijk paths. These are exactly these paths where we have a unique peak of maximum height. Okay, why are we interested in those? Well, because apparently Miklos Bona and the student Elia de Jong were interested in whether the ratio of these paths among all of them is decreasing for n greater or equal to 3. There's a reason why they're interested in that in particular, namely has to do with 1, 3, 2 avoiding permutations with a unique longest increasing subsequence. That will appear in the very end when I can answer that question actually. But anyways, this is the question that we would like to study somehow. Okay, direction is correct. Good. Why or how can we tackle this? Let's talk briefly about enumerating those. We can take one of these paths. Now I was too slow. There it is. We can take it. We can flip the second part and rotate it around and see that each of these max peak unique paths actually corresponds to 2 paths that start in the bottom, act like Dijk paths, so they don't go below the axis, and the end at their highest point. These paths have been referred to as culminating paths. And curiously, this also allows me to answer a question, or at least a comment that Daniel made in his talk 2 days ago, where he said that Clemens in AofA 2015 gave a talk on some sort of lattice paths. Those were the paths that Clemens was talking about. And I have no shame in borrowing Clemens' slides from that particular day. So all of you that were there and listened to the talk surely remember how everything is set up. But here's the actual result from that day. The probability of such a path is given essentially by this coefficient of z to the n plus 1 in this expression here, where u h plus 1 is the Chebyshev polynomial of the second kind. So these appear here. I don't give any details. The setup is basically you can write down the recurrences for these paths in sort of a transfer matrix, and then, well, do the usual stuff and get this expression here out. Okay, so we have that. Thanks, Clemens. We know the ordinary generating function of one of these, so we can actually piece 2 of them together, like we usually do, and have this first little result here for the ordinary generating function of these max peak unique Dijk paths. Okay, so far so good. The next part is also not too arcane and something that I think most of you have dealt with in some setting already. We simplify this a little bit or rewrite it a little bit using a substitution, namely with these 2 rules here. I again you don't have to do the details by yourself. I'll just show you what comes out. We can rewrite the generating function after setting x to the square root of t over 1 plus t in this particularly nice form that's the sum of rationals. And from there, after some more magic involving, well, basically taking contour integrals or Cauchy's integral theorem, we can extract the coefficient and give an explicit formula for this one, namely this nice expression here. Okay, so far so good. We found the exact enumeration formula for these particular paths. And just to remind you, we are interested in whether the ratio of these paths, so this here divided by the nth Catalan number, whether this is decreasing for n greater or equal to 3. Sigma is the summatory function of divisors. It comes out after, well, basically extracting this thing over here. It doesn't matter so much right now. Okay, so this is what I just said. We were interested that the question that was posed in the beginning is equivalent to this sort of inequality here. And well, we have an explicit expression for A, so let's just plug that in here, multiply things around, and shift a little bit, shift stuff a little bit, and then we have an equivalent question, which is a little bit nicer to look at than the written out part before, namely, this sequence here is decreasing for n greater or equal to 3, if and only if this expression here, so it's just a sum from k equals 1 to n, k times sigma of k times this polynomial factor here times binomial coefficient to n, choose n minus k, when this is negative for all n greater or equal to 5. Okay, this is something that's quite nice at this point, and something we can deal with asymptotic methods the, well, more or less usual way. We try to approximate this here somehow, split the sum in different regions, do some sort of Mellin approach, and in the end get out asymptotics, right? That's what basically is happening on this slide here. And if we do that with standard methods, then we get out that the asymptotics for Fn is binomial coefficient to n choose n, times this expression here, and note the minus in the dominant term. Everything is nice. You would think it is, but actually this sort of thing doesn't give us enough information. We only know that the sequence that we have is eventually decreasing, but that's not what we want to have. We want to know, is it decreasing from n greater or equal to 3 on, or for at least this function here for n greater or equal to 5. So what we need is more information on that guy over here, the little o of n. And this is something that's said very easily than done. In theory, you know, okay, we have all sorts of inequalities. We can plug in things, and in the end, it's certainly possible theoretically to get out an explicit constant that bounds this term over here. Well, let me tell you, if you try to do it by hand, good luck, because it's actually really, really, really tedious to do all of these expansions and keep track of what is important at which point. So no, nothing nice. It's we've tried. Actually, we've tried whether we can see some sort of more or less obvious, or so less obvious, to be honest, recurrence for this guy here, but there was no real chance of getting anything that was helpful. Oh. Okay, wrong button. Okay, so that was Act 1. I hope I gave you some sort of motivating example why we want to have more information on the error terms sometimes. And to do that, I'd like to introduce an auxiliary concept. I've spoken about this at previous meetings before. I'll actually call them B terms now, which is sort of a explicitly bounded version of O terms where you know the validity point. So this term here, capital B of n greater or equal to 100 of 42n cubed means this expression here is bounded by something that is valid from n greater or equal to 100, bounded by the expression 42n cubed. Okay. We have written a package, it's called dependent B terms in Sage, that extends the existing implementation of the asymptotic, the modules for the module on computations with asymptotic expansions. And basically this thing does two things that we could not do before. The one thing is we have an additional variable that's monomially bounded between the variable n that is assumed to go to infinity, which is useful for these sort of computations in the sum. And the second one is Taylor expansions with and at these expressions that involve these B terms. If you want to use it, there's the one-line command that you need in your terminal, or you can also try, if you really want to play around with it instead of listen to me speak about it, there's this short link bhackl.dev/asi/dbt, or there's also a static version you'll find online if you just type in dependent B terms, and you should find everything. Okay, let me walk you through how this works briefly. This is basically how you initialize one of these special asymptotic rings. You basically say you have expressions that look like n to the power of some rational. You have an additional variable k in this case, which is bounded between n to the 0, so 1, and n to the 4/7. For the b terms that appear here, it sort of turned out to be convenient to build in some sort of automatic rounding, because there's a lot of weird symbolic manipulation going on, and in the end, you'd actually just want a numeric constant. So doing that immediately means that the computer doesn't have to struggle so much with extremely large symbolic constants, which is a pain, actually. So we have this one here, and we have some sort of default position that is used when terms are expanded automatically. Okay, so we have this. And then we can look at examples of how this thing works, actually. The first one is actually already a fun one, because here you can see I specify an expression as k times n squared plus big O of n to the 3/2 plus k cubed times n. And in any normal world, at least in the world we had before, the order of these would be, well, the strongest growth comes from n squared, then that should be first, then the next one comes from n, and the last one is the O term, which actually should eat this guy, because that's O to the O of n to the 3/2, and that's just O of n. But if you have a dependent variable in there, that skews everything. So instead of having an exact growth per summand, you now have some sort of interval that you have to deal with. And that complicates things both in the display of the expression and in what is actually allowed to absorb what. In this case, you can see the three summands that you have here, and you can see the lower bound that each growth element has, and the upper bound. So this here, the lower bound is n squared, because the k could just be close to 1, or it could be n to the 18th seventh, because for some reason I chose sevens as an example here. Well, whatever. This fits nicely and works out so far. One thing, and this is the sort of one example that I want to briefly discuss. How does arithmetic like this work now? It's actually relies on really, really crude estimates, because that's all I had time to implement so far. If you want to add this guy and this guy, the first thing we have to check, can this b term here absorb this exact term? And just from looking a little bit, there's an n cubed here, there's an n to the 5 here. So maybe if the powers of k also fit, if you don't want to do it in your head, I actually did it before. The b term here has a growth of n to the minus 23/7, and this guy over here, this guy over here has a growth of n to the minus 23/7, and this guy over here can definitely eat that guy. So we can put this guy in here. The question is just, how do we do that exactly? And the answer to that is, well, first step, we get rid of the weird sum in the numerator up here. So we have this sort of crude bound over there. And then we use the given bounds, namely we know that k is less than or equal to n to the 4/7, and we know that n is greater or equal to 10, to do this sort of magic here, to arrive from this expression over here, that was an upper bound for this here, we arrive at this here, which is compatible for addition with this guy here. And this is all the things that happen internally in basically every step of the computation. So, and if you now ask Sage to compute this expression here exactly, then it will tell us it's 3,373 over 1,000 times absolute value k squared n to the minus 3. Absolute value is not necessary, but well, it put it there because it's hard to get rid of that one, actually. Right, and this 3,373 over 1,000 is already one of these rounded constants that appear, because otherwise we have this guy here, which is not that much fun to compute with. Okay, so that's one example of B-term arithmetic. I will skip over this. It's basically, well, I sort of skip over this. It shows you how we can simplify expressions sort of automatically. Actually, let me say that. If we look at the automatic expansion of the exponential here in 1 plus k over n, then you see all it does is the usual thing, namely it plugs in powers of 1 plus k over n and weighs them correctly and sums everything up. But it does not do automatic expansion of these expressions to absorb all the terms that can be absorbed safely. you have to kind of tell the expression that it should do that. This is basically something that we did for performance reasons. So collect terms that look large and ugly until some point where you collapse everything and then it's nice again. Right, and the other thing is, well, we can do Taylor expansion. That's actually not that exciting. It's just, well, we implemented it. If you try to do, what did I do here? It's this expression here, 1 plus k over n plus a b term in k to the 3 over n to the 3. We take the Taylor expansion of 1 over 1 minus t squared of order 3, some sort of validity point, then we get this sort of expression out. It's, well, it looks a little bit messy, but it's actually nice to have something that can do this automatically, because I for sure don't want to do that by hand. Okay, speaking of things that I do not want to do by hand, let's get back to our example. I'll briefly finish so that we don't take too long for the coffee break.
Take your time.
This part, so Act 3 is actually the part where I do lots of hand waving, because this is the part where we combine this package that I just showed you with the problem from before. And as you will see, the things that happen, on the one hand, really underline that you do want computer algebra for this, because it's very tedious to do this by hand. I don't think it's actually really possible or feasible to do, at least if you follow this approach. Okay, so first step, we fix an arbitrary number of capital N, which is sort of the bound from where we want our the bound for n from which the asymptotic expansion should hold. So at that point, we want to have asymptotics to take over, and we check this inequality here, this f of n, the sum that you saw a few slides before. We check that this is less than 0 for between 5 and capital N. We do this by, well, the direct approach. Just let the computer do it, and in the end it says true, which, well, great. Next step, we have this sum, and we identify the regions of the sum that do not contribute a lot. So a negligible amount, but again, we need an explicit bound for that. So we split this sum that we have. First of all, we normalize by a factor of 2n choose n. And we split the sum that we have over the region from 1 to n into 3 different regions, actually. One region where everything is very simple, in that case where we are already past n over 2. In that case, this ratio of binomial coefficients can be expressed by a b term. That's actually really not, that would be one that I could do by hand. 52 choose over 25, exponential decay here, linear exponential decay here, and some polynomial times log n. The second part is a little bit more fancy. Basically, we take the sum, we choose a value of alpha, which is in this case 7/10, and we consider the region from n to the 7/10 to n half. So the part that comes before, so to say. In this region, we can still probably work out things by hand mostly. I think Stefan did actually. In this region, we can bound the sum that we have directly by this expression over here. So some constant log n times the sum over, well, actually k greater equal to 0, and this expression over here. And then you can use an integral estimate to get the actual asymptotic bound for that case. So this is, well, some nice constant. Again, we have sub-exponential decay, but still something that decays fast. And again, some sort of polynomial times logarithmic time. Okay, so that's we threw away the tails. Next step, all right, I wanted to show you that you can throw these things into the package and it will compute these constants for you automatically. The thing that does not work, and I should say that, is these special terms I had here, e to the minus n to the 2/5 and the log factor. That's actually not really supported, so you have to carry those with you sort of manually. It's annoying, but it's better than doing everything by hand. Right, so that's that. The next part, well, now the magic starts. We need an expansion of this guy over here. So we are now in the region from 1 to n to the alpha. And in this region here, we need an asymptotic expansion, an exact one, so with bound coefficients, that looks like this. I've purposely shown you only the first 3 terms of this expansion, because if I show you the full expansion, that would look like that. So this guy starts here and ends over here to get the precision that we actually need. You can see there's a bunch of these B terms already in there. There's not a lot of automatic absorption going on. If we would say, let's collapse everything, get rid of the K's in these B terms and look at how the expansion really looks like, then this would be the collapsed version of it, so to say. So this is this. Right. From this expansion, we have some parts that actually correspond to errors and some parts that are exact. We deal with the error ones first and collect the contribution, if we combine everything back together with the sum of this fancy number here, 14,600 times square root of n times log n. This is actually much larger than the errors we had before. There's no sub-exponential decay anymore, but still nothing too bad. The third part, the exact part, we complete the tails for that again. So this is again two summands that contribute sub-exponential decay, which we don't really care about. It's tiny compared to this error here actually. You'll see the combination of all the errors at the end. So that's this part, and then, well, we extract asymptotics. And how do we do that? We compute the Mellin transform, we use converse mapping, we shift the line of integration to the left, and collect the residues. And as you might be able to tell from this spinning emoji here, that's something that can make you dizzy if you do it by hand, because the Mellin transform looks like this. It's not the nicest transform I've ever seen, but it's also, I think, not the worst, coincidentally. The main term, if you extract if you shift the line of integration to the left and collect the residues, gets you to minus n squared over 8 plus n to the 24, which is exactly what we had in the beginning. So that's very nice. And the part that I want to emphasize here on is this thing here looks, if you look closely, there are these combinations of gammas, zetas, and zetas. This looks a little bit bad. It's not too bad actually, because it's still fairly structured in the way where the singularities are. But what does happen is there's heavy cancellation in the results. So it's actually not easy to see from this sum over here. I mean, what can you see from this sum actually? But it's not easy to see that the order would be n squared from just this part over there. And then the last fun part that we had to do is we had to estimate these shifted integrals numerically somehow in order to get the remainder of this bound. We chose to do some sort of interval arithmetic integration in the interval within, I think it was from in the strip from minus 100i to plus 100i, and beyond we used a more or less crude estimate again, because the gamma function is there and causes fast decay beyond. Yes, that's what I told you. And the error that we collect from that one is 4,000 something times n to the 3/4. If we now collect all of these errors, so if you paid attention, we had errors from pruning the tails, we have errors from the central expansion, we have errors from adding the tails back, we have errors from this last part over here, and I'm sure I forget something, but it's not so important. If we do that, then we get one exact B term for this entire sum, and it is 7,751.1106 times n to the 3/4. At this point, if you have not, the thing that we did is, well, is this already enough actually? Can we look at this and see, does this guy win against this guy, or is our main term already strong enough? And then we started plotting things, and the red line you see is the magnitude of the main term, and the blue line that you see is the magnitude of the error, which means that about after n is 7,000 or so, the main term wins, and we have a certificate, we have a proof that this sum here is actually negative for all n greater equals to 5. The bonus, the result that follows from this is for any length n, there's at least as many 1, 3, 2 avoiding permutations with a unique longest decreasing subsequence as those permutations that do not have one of these. And with that, I want to thank you.
So one quick question, maybe.
So at some time you showed the slides by Clemens, where there was this enumerative results with the 1 over the Fibonacci, the Chebyshev polynomials, and there was a formula quite similar by Bouchke-Mellou and Ponty for cumulative space. So what is the difference between this result and the result of?
I should have mentioned that point. I wanted to say it. These paths have been examined before by Bouchke-Mellou and Jan Ponty. And in a paper of ours, it's exactly the same thing. So it's just like a minor rewriting of these things here. That's exactly the same. The paths that I enumerated here are actually those that have not this. They have a slightly weakly property in the sense that they end on the weak maximum of the path and not on the.
So you could reach the maximum several times.
We could do what? Sorry.
Here you could reach the maximum.
Yes, in these one
several times.
Yes. In this one I can reach the maximum several times. And the way how you repair it is you append one step.
Yeah, for sure.
Okay.
So why 10,000? You could easily verify up to 1 billion. Would it help to do B of 1 billion or?
It would have helped to get the constants down a little bit, but actually, if you don't want to spend too much time on evaluating the sum, I think, let me see where I have it. There it was. This one took already 11 minutes or so on my desktop, and that was the point where I just wanted to have this evaluated, then do some math to do the rest. But it would have been possible to shift this point and bring the constants down somehow. Clock time. Yeah.
So we'll take the last questions and then the rest in coffee break.
So this is very nice. At one point you said you have a certificate. So in what sense is it a certificate? I mean, can you give it to a user and can he check it?
Certificate is indeed the wrong word. I shouldn't have used that. Certificate only in the sense that it's a certificate for the inequality in some sense, but not in the sense that there's some quick way you can verify that this has to be true. That's unfortunately not. No. Thank you.
Well, let's thank Benjamin again.